So the compulsory reminders. One is that there's the possibility of gathering at GatherTown after the talk. I put the link in the chat. Let me discuss the protocol also before we get started. So questions, as usual, are welcome at any point. Everybody should be able to speak at this point because everybody has been promoted to panelists. It's still nice because people might join as attendees later. If you're sending a chat message, make sure to send it to all panelists and attendees, because otherwise the attendees won't see it. So you can ask questions in the chat. You are also, and then I will try to read it out to our speaker, Bart, at the first suitable moment. But it's also fine, and it's nice to have some interactivity. Just unmute and ask your question as you would as in a regular seminar. So I don't think I have anything else by way of formalities. We've had different setups for different talks. Today, I think we're looking at one seminar that is probably, so if I understood Bart correctly, roughly an hour or slightly more without questions. But of course, we'll try to add lots of questions to make Bart speak with us for longer. But it's not like a clear first half, second half kind of thing. It's more like a unified seminar, probably. And with that, I'll do an extremely brief presentation of Bart. Bart, who's at the Vrije Universiteit Brussel, which I'm not supposed to translate. That's the Free University of Brussels. So I didn't say that. We had a complicated discussion just a few minutes of you, for those who heard, that what the Free University means. And there are apparently several free universities in Brussels in different languages. But Bart is at VUB, where he's interested in knowledge representation, at all kinds of levels. For the SAT community, maybe one of Bart's claims to fame would be that he's one of the people behind the SAT solver with symmetry breaking that won the 2016 No Limits track in a breakaway fashion. But Bart is not going to tell us about that today. He is going to tell us about an intriguing topic of explainable constraint programming, kind of, sort of. And in order to understand what that even means, I'll have to leave the word to Bart. So please.
So thank you, Jakob. So indeed, I will talk about a framework for explaining how to solve constraint satisfaction problems. But I actually, or you lied maybe unknowingly. I will talk a little bit about symmetry in my introduction. Because when I was first asked to give a talk here at the Beyond Satisfiability workshop, I thought, well, beyond satisfiability, so where should the satisfiability community go next, in my opinion? So what's important? And then I always think of, it's this paper by Peter Stuckey at some workshop a couple of years ago, I think, which was titled, There Are No CNF Problems. So, and what he meant by that was, well, there are no problems that are naturally in CNF or anything. I mean, we're always encoding some problems at some higher level that arise more naturally at a higher level. We're encoding them as CNF, and we're developing very efficient solvers for that. And so an obvious way for going beyond satisfiability would be to adopt some sort of high-level modeling language, which is done typically in constraint programming, but in many other disciplines as well. And the reason why is because when solving set problems, we're actually missing structural information of the problem often. And our work related to symmetry breaking really highlights this problem, that what we've been doing there, our main focus of the work was on detecting structure in the problem. Structure that was there in the modeler's mind. So the people who were solving this problem, they knew that this structure was there. they modeled it, and then they wrote some encoding to CNF, and then the structure was lost. And then this problem is given to a set solver, and it's asked, well, solve it. But I'm not going to tell you about the structure. And this is, of course, not the efficient way to solve it. So we spent lots of time optimizing the symmetry detection, figuring out that actually this CNF encoding is an encoding of some problem at some higher level in which certain objects are interchangeable. And this fact that there were some interchangeable objects at a higher level allows us to get really good encodings of the symmetry breaking constraints, compact encodings that have very strong breaking power. On the other hand, if you would give a solver, instead of giving him the CNF encoding, give him a first order representation of the, say, a pigeonhole problem. The prototypical example of this symmetry breaking is pigeonhole. So if you would give the solver a first order version of it, and you say, well, for all pigeons, there must exist a hole such that the pigeon is in the hole. And for all holes and two couples of and two pigeons, if they're both in the same hole, then they must be equal. And then you give it a set of pigeons and a set of holes, then it's clear for the solver that these pigeons are interchangeable, the holes are interchangeable, and no detection is needed. And the pigeonhole problem becomes very easy. So a good step forward for the set community would be, I think, to adopt a single higher level modeling language. But of course, which one do we need to choose? And that's a difficult question, because this choice is causing a lot of fragmentation. There's lots of different research domains that go beyond SAT and that well, are using different modeling languages, but actually using a lot of techniques from SAT. That's just my small message. And in today's talk, you will see this. So my algorithms that I will discuss will all be at the SAT level. So I will talk about propositional theories and some algorithms for them. But the explanations that I will produce will be at the first order level, at the kind of types of constraints that you would write in the context of constraint programming. And actually, internally, it also works like this. So we're using this type of first order constraints, but we're grounding them, we're reducing them to CNF, but we still have the first order constraints, and the explanations that we will produce, that we will give to the users, will be in terms of the first order constraints. So if at any point during my talk something is unclear about, well, now you're showing me first order formulas and then you're doing stuff with propositional logic. On the other hand, if at a certain point the relation is unclear, just interrupt me and we can go a bit deeper into that. But so I will switch between the two levels sometimes. So that might be confusing, maybe not. So just interrupt me. And actually that holds for anything else as well. So if there's any questions, feel free to interrupt me by voice. It's the most efficient way of communicating. It's much faster than typing. So, and I when I teach, I already talk to a non-responsive screen way too long. So just interrupt me. So what's on the agenda for today? So I will present some, actually a quite young research project. We started somewhere last year to work on this. And the project was originally triggered by the Holy Grail challenge, which was a challenge at a CP workshop on progress towards the Holy Grail. And this challenge had to do with solving zebra puzzles. These are zebra puzzles are also known as Einstein puzzles. These are puzzles in which you get some clues. I'll show some examples in a minute. Some clues and have to match certain entities together. So there was some challenge there. We tried to solve it, and that's actually what led to this whole project that we're working on now. And on explaining basically solutions of CP problems. And so I'll talk a bit about this challenge, what the challenge was, what the puzzles are, and then I'll talk about our solution that we had for explaining them, which was stepwise explanations. This is published at ECAI last year. And then in the later parts, I will go into some, well, unpublished work. I will, in part 4, section 4, will be about the OCUS problem, which is somewhat similar to minimal unsatisfiable subsets or smallest minimal unsatisfiable subsets, which you might have seen occur somewhere already. This is work that's still under review. And then in the 5th section, I will talk about nested explanations, which is about explaining at different levels of abstraction, basically, you could say, or certain explanation steps that we will produce in section 3 might still look quite difficult. But we then want to zoom into this to really explain it in more detail by means of some form of reasoning by contradiction. And then finally, we will conclude. So first, about the Holy Grail challenge. The Holy Grail challenge was about logic grid puzzles. And in these puzzles, you always have a set of clues. Set of clues are just sentences in natural language. And you have a set of a set of sets of entities. So you have some sets of entities, and you need to link these entities together. And so the most famous example coming from Einstein is about a zebra and an Englishman living in a red house, and the Spanish smoking cigars, and the one person living next to another one, and then you need to figure out all the relations basically. And so each entity is linked to exactly one entity of each other type. So for instance, in this, I'll just give an example on the next slide. And all the links are consistent. And this I will refer to as transitivity. And the fact that each entity is linked to exactly one other, I will refer to as bijectivity. So here's a small example. It's about people who went to a restaurant together. They all had pasta. So they had a different type of pasta. Each person had one type of pasta. Each person had one sauce. And they also had to pay something. They had to pay a certain amount of money. And then there are some clues in natural language, such as, well, the person who ordered capellini paid less than the person who chose arrabbiata sauce. The one who ordered tagliolini paid more than Angie. Angie is one of the persons. So the one who had tagliolini paid more than Angie. So we already see that Angie will not have ordered tagliolini, and so on. So there's a set of clues here. And if I, as a human, want to solve this kind of puzzle, how would I work? Well, typically, these puzzles also come with some sort of a grid. Let me zoom in a little bit so that you can read it well. So typically, they come with some sort of a grid here. And you will start filling in things, in this grid. You will start filling in, oh, well, the person who ordered capellini paid less than the person who chose arrabbiata sauce. So definitely capellini and arrabbiata sauce will not be linked together. And you can put some cross there. The one who ordered tagliolini paid more than Angie. Well, if I use that clue, there's lots of stuff I can derive. Well, so Angie didn't order tagliolini. So Angie didn't order tagliolini. And then I have to find out where that is. Angie didn't order tagliolini. But also, Angie didn't pay the largest amount. And so the prices were 4, 8, 12, 16 here. So Angie cannot have paid the largest amount. And I can keep on doing this. I can keep on filling my grid, going over these clues, seeing what can I derive. Basically, I'm doing some sort of propagation here. And sometimes I will also use these implicit axioms. For instance, once I have derived, and this is now not correct, or not necessarily, once I have derived that Angie didn't pay 8, 12, or 16, I can derive, okay, in that case, she must have paid 4, of course. And then I'm using this bijectivity constraint. And if I want to use this kind of transitivity constraint, what I would say is, well, Angie, she paid 4, but she didn't take tagliolini. So tagliolini cannot have cost 4. So let me use my colors consistently. So tagliolini cannot have cost 4. So that means that these links are consistent. If Angie paid 4 and tagliolini, she didn't take tagliolini, then it cannot have been the tagliolini that cost 4 euros. Okay, so these are the logic grid puzzles. And then there was this challenge. And the challenge consisted of 3 parts. The first part was parse these puzzles. So do some natural language processing, parse the puzzles, and translate them into some constraint satisfaction problem automatically. The second challenge was solve this constraint problem automatically. And the third problem was explain actually, I think it was stated, explain in natural language how to solve this puzzle. So it was quite related to natural language, but we were lucky. We were lucky because a couple of years ago, one of my master students, Jens Klaas, he had for his master thesis worked on the problem of translating logic grid puzzles from English into first order logic. So step one, basically, we got for free when this challenge was announced. And step two, well, it's not really a challenge. And these puzzles, they were made to be solved by humans. So solving them automatically for a computer, once you have a formulation, it's really no big deal. So this was also solved. So we focused on the explanation part. By the way, this parsing into natural language, it's an interesting challenge. Our solution was not completely automatic. I think there was some tagging of certain words that needed to be done manually of the entity. So it was mostly automatic, but not completely. So there was some intervention needed. But I'm not going to focus on that. I'm not going to focus on the natural language aspect, except for one thing, that sometimes I might show you some of these translations into logic, and they might really not look like what you want to do there. They will all use binary predicates. They will not use functions, for instance, while actually this is a problem where you're searching a lot of bijective functions. But we will make no assumption of how they are represented. I think if you go tweak your representations, you can make everything much more efficient, but we didn't do that. So we just started from what the natural language processing tool gave us, these logical sentences, and we didn't touch them anymore. We will see an example of that. So our focus was on this explanation. So how can you explain to a human how to solve this puzzle? And these explanations, they're typically, well, what we aimed for is basically what I've been telling you. So we aim for a kind of an explanation that says, well, now you can use this clue together with these previously derived facts to derive new facts in your grid. And our first version was in natural language, where all these arguments were given in natural language, because technically that was a challenge, but it became very unreadable. So instead, we went for a visual explanation, which is basically what I already showed you. This grid here that gets filled in automatically, in which we then highlight, well, if you now use this clue, and then there's in our interface that I'll show later, there's also, you now use this bijectivity, or you use this transitivity, or sometimes you even use a combination of bijectivities and transitivities. But every time we say, well, if you use this clue or this implicit constraint, as we call it, and you use these previously derived facts, so maybe I'll just show an example. So this is the same puzzle as we've been seeing before. The first thing he derives is the same as what I did here. I think the person who ordered capellini paid less than the person who chose arrabbiata sauce. I know it's something else than what I said, but what you can also, was that also my first clue? Oh yeah. What you can also get from this clue is that arrabbiata sauce cannot have cost 4, cannot have been the smallest price, because the person who ordered capellini paid less than the person who chose arrabbiata sauce. And we continue like that. We highlight a certain clue gives us some information. So this is exactly the same as what I had said in my explanation. NG cannot have bought tagliolini, and NG cannot have paid the most because of this clue here. And it goes on a bit like this. And after a while, you will see that you cannot not just use the clues anymore, but sometimes you will say these blue squares here, they indicate, well, I'm using this previously derived fact that arrabbiata sauce was paired with farfalle. And I use the bijectivity constraint here to derive that, well, if it was paired with farfalle, then it was not paired with any of the other pastas. So these are the kind of explanations we produce. And here's this transitivity constraint. It's always this triangular pattern where we say, okay, arrabbiata sauce was paired with farfalle, and Claudia did not choose arrabbiata sauce. So yeah, she cannot have eaten farfalle. And it goes on like that. And after a while, the explanations will get more complicated. But now let's formalize this, okay? So I can show you explanations. You can, yeah, we won the challenge, but that's maybe not such a big thing to say because it was out of 2 participants. So I should also mention this, of course. And I think the reason why we won is because we had this holistic solution. We tackled all the different pillars, thanks to this master student who had already done most of the work for the natural language part. So we saw the demo already. And basically what we're doing is, I already mentioned, we're not going to tweak the representation. We're also not going to modify the underlying solvers. And we're also not interested here in explaining how the solver found the solution. We're not trying to explain how a certain solver works. What we're aiming for is to find an explanation that is useful for the human. And the human probably doesn't care that the solver started making some choices instead of propagating or whatever he's been doing. The human knows these puzzles. He doesn't need to know any solving technology. We want to explain to him how to solve the puzzle. So you can check this demo on the website. So after developing these ideas of what kind of an explanation we wanted, we said, okay, we want to formalize this. What is an explanation? How can we compute it? Yeah, how can we guide the search for these explanations and demonstrate that it actually works? And that's roughly what we did in our ECI paper. So I will often use sigma to denote a propositional vocabulary, and a partial interpretation is a consistent set of literals over sigma. And sometimes I will also identify this interpretation with a set of unit clauses. So I might write, if T is some propositional theory and I is an interpretation, I might just write T and I to denote the new propositional theory consisting of everything in T and then all the unit clause of everything that's true in I. So a propositional theory is a set of constraints. I don't care if they're clauses or if you have some other propositional constraints. And so again, slightly abusing notation, but this is quite common. I don't think I should say to this audience a set of constraints I identify with the conjunction of all of them. If I say this, T and I implies I prime, it means that all models of this are more precise than this. So that all the information I prime follows from what's in T and what's in I. So this is quite standard. So now the goal of our explanation problem is the following. Or maybe I should say this, these logic grid puzzles, they have the very nice property that they have a unique solution. So there's a single unique solution that's implied by all of these clues. And so our goal is, given a set of constraints, T, and maybe some interpretation, I, we logic grid puzzles, that's the complete solution. In other cases, this might just be, well, what can be derived by some very strong propagation mechanism. So it's the intersection of all the solutions. It's the cautious consequence, sometimes called. But so our goal is to explain how you can start from T and I and get to I end. So to this final end for the logic grid puzzles, nicely and also for many other of this type of puzzle games, this is just nicely the unique solution. So the way we want to do it is we want to break this explanation in simple steps, simple in between quotes. I still have to say what simple is. We want to explain in simple steps how to go from T and possibly an initial interpretation already, which you can also assume to be part of T, but to go to this cautious consequence. And our focus until now has always been on single steps, on saying, okay, what is an explanation step, and how can we compute good explanation steps? that are simple, in between quotes. And we're not focusing on aspects of optimizing the entire sequence yet. For instance, for humans, it might be much more logical to say, to first derive everything you can do with one constraint before you jump to the second one. So the order in which you derive certain things might be relevant for humans, while we haven't been doing that yet. So our focus has been on how can we find a next very simple step to explain, and then the next one, and the next one, and then chain it into a sequence.
Art, a question?
Yes.
Are we always interested in like facts, which I guess in SAT language are unit clauses, or can we derive more complex, like we know either this or that, or no? We're looking at units.
We're looking at well, unit clauses or facts here to explain. No disjunctive knowledge, no complicated knowledge. Actually, you could play with that. I mean, by changing your language, you could introduce a new variable that represents some form of disjunctive knowledge, and in that case, you could go derive it. But we went for the facts because it's very easy to visualize, and basically, you could also you could also restrict your vocabulary on which you're allowed to explain. So depending on we don't really do it yet currently. Well, technically we do it, but it's not so visible. And that has to do with my very first remark. But so you could restrict your vocabulary of even which literals you're allowed to use in your explanation, which ones you're allowed to derive, and which ones not. And the reason why you might want to do this is because what we do is we have this first order logic representation, and we reduce it to SAT by grounding. But that will introduce lots of auxiliary variables, and these variables we don't want to go use in our explanations because the user doesn't know them. He doesn't know what variable 20,507 means. So giving an explanation of the form, well, now we can derive variable 20,507 is not very useful for the user. So we only want to explain it in terms of things he can understand. So in our case, the things he can understand, we decided for the logic grid puzzles, it's the grid. So the only thing that you can use for these puzzles in your language of explanation, if you want, are facts like this is true in the grid or this is false in the grid, things you can actually mark in the grid. These are the things we as a human would probably also be reasoning with. So yes, only facts. But if you have a smart user who knows about disjunctions or stuff like that, you can change your vocabulary and also allow for these new facts to be used in your explanations. So now, formally, what do we mean by an explanation step? So if we have at a certain moment found this interpretation here, I minus 1, and we want to go to a more precise one that has a bit of extra facts in it, I, and the next one in the sequence, we say that, well, how can we explain this step from I minus 1 to I by a triple? We say we explain it by a triple, where Ni are just the newly defined facts. We have them in the triple because they're sometimes useful, but mainly, so what's really explaining it is, well, in order to go from here to there, we have some certain previously derived facts that we're using. And there is a typo. This should be I minus 1, I see. So we have some facts from the previous step, what we already had derived so far that we were using. We say we're using a certain subset of the clues. So clues and implicit constraints are in T, so we're using a subset of those. And well, they should be so that indeed that subset plus these previously derived facts entail everything that's new. Of course, this is a very useless definition still. This is just basically giving some correctness criterion of when we say that indeed these subsets explain something. So we probably want to do something better than that. We want to look at non-redundant explanation steps. And a non-redundant explanation step is basically one that you cannot shrink anymore. Saying that, well, if I would have some subset of my previously derived facts that I'm using and some subset of my constraints that I'm using, and that still explains this derivation, well, then it must be so that they are equal. I cannot have any strict subsets. So that's some form of non-redundancy. And that's already good, but it's probably not enough. Maybe here's a first observation that, so if we're interested in computing these non-redundant explanations, we can actually use an existing technique, minimal unsatisfiable core or minimal unsatisfiable subset extraction, because there's a nice correspondence between minimal unsatisfiable cores of a certain theory and non-redundant explanations of, oh, there's another -1 missing here. I was a bit sloppy, it seems. So there's a nice correspondence between minimal unsatisfiable cores and non-redundant explanations. Namely, if we have a minimal unsatisfiable core of this here, this says, well, what I previously had, and that's another -1. So lots of off by 1 errors, it seems. If what we previously had and the theory and not L, so not the negation of the literal we want to derive, minimal unsatisfiable cores of this, first of all, they will always, since we're working in a satisfiable setting, they will always contain not L, these minimal unsatisfiable cores. And whatever they contain of I -1 and T exactly forms a non-redundant explanation to go from okay, no, here my -1s were not really needed because here I just had my next one was I union L. So here it was actually okay on this slide. So I will start over. Minimal unsatisfiable cores of this theory on the left correspond to non-redundant explanations to go to derive one new literal, L. And that was an observation that was quite handy for us because the tool we were working with, that's the IDP system, that supports first order logic and grounds it to SAT basically. It already supported minimal unsatisfiable core extraction as well. So here was something we could work with. Any questions about this correspondence? Is it clear, or should I explain this in a bit more detail? Okay, I assume it's clear, but just come back to it if it's needed at some point. So I already said this non-redundancy is probably not good enough. We will assume some cost function, and what that cost function has to be, we don't really know it, but we just assume some generic cost function that quantifies how interpretable an explanation is. Because, for instance, in these logic grid puzzles, you could easily get very bad minimal or non-redundant explanations. If you have something like, well, this here, 8 is linked to arrabbiata sauce and farfalle is linked to arrabbiata sauce. Well, the obvious thing to do is, well, for instance, then 8 is linked to farfalle because of one transitivity constraint. But actually, you could also get this indirectly because of using 5 other transitivity constraints together. And that's not the kind of explanation you want. You want the one with the one transitivity constraint. That just directly says this transitivity constraint together with these two facts gives you this new fact. So non-redundancy gives us bad stuff still, so we need some cost function. And so what we're aiming for then is to produce some sequence that starts with some initial interpretation and that derives at each point a new interpretation and this is the explanation of why it follows from I0. some sequence, and we want to minimize some aggregate over this sequence. And for now, I said we're not really working on optimizing the sequence as a whole yet. So we're basically, what we're now minimizing is the hardest step in the sequence. But there's lots of room to play with that as well. And how do we do this? Well, I already mentioned we have minimal unsatisfiable subset extraction. So our first bet to solve this was, let's just try to use it. And what we did was, so I'm showing you here how to compute a single step. So we have arrived at a certain interpretation I, and we have this theory here. We want to get eventually to I end, and we have this cost function here. And what we're saying is, well, we'll just go over all of our literals that we still need to derive. We will compute some a non-redundant explanation or a minimal unsatisfiable subset of how we could derive this single literal, and we will just pick the best of them. And let's hope it works. And of course, we ended up, if we really just do that, we saw this is sometimes giving terrible things because of the kind of phenomenon that I just mentioned, that sometimes he picks 5 transitivity constraints, which indeed form a minimal set, but there's actually one that would be a much better fit. So, and also, yeah, this minimal unsatisfiable subsets here, this guarantees that we will find something non-redundant, but we really have no guarantee about the cost. So we're just hoping that we accidentally find a good one. We could solve this by enumerating the musses or by optimizing them, and that's actually what I will talk about later. So for now, what we see is, well, we have a guarantee of non-redundancy. It doesn't really guarantee quality. And in our ECI paper, we basically worked with the tools we had and tried to optimize this as much as possible. So to have some heuristic workarounds that actively go search for smaller sets of constraints that could derive something. But I will not go into the details because I think by now we have better solutions. So details are in the ECI paper. So what else we did back then is we implemented this, of course, and we have some visual explanation interface. I already showed it to you. And we also made up a cost function for these logic grid puzzles. And we put some numbers on it because, yeah, if you want a concrete cost function, you have to do that. But these are really just magic constants, right? For instance, I think we said that, well, using a single implicit axiom like a bijectivity constraint costs 5. Why 5? Because it just seemed suitable to us. It's future work to really evaluate what's difficult or what's conceived simple and difficult for a human, but this is really something we didn't focus on. So we just said, okay, using a single implicit axiom is very cheap. Using a single constraint together with some implicit axioms is less cheap. And using multiple constraints or multiple implicit axioms is very expensive. Of course, if I show you this list, you might wonder why not use a single constraint without any implicit axioms, because we've been doing it all the time. But actually, it turns out that because of this, and that's a side effect of having no control over the encoding, it almost never happens that you can use a single constraint without implicit axioms. For instance, from this clue, the person who ordered Capellini is either Damon or Claudia. You could immediately, a human could say, well, only using this clue, I can immediately derive that Angie didn't order Capellini because it must be Damon or Claudia. But our translation that we got, this first order logic translation says, there is some person who ordered Capellini and who is either Damon or Claudia. This in itself doesn't entail that Angie didn't order Capellini. It only entails it in case you have this bijectivity constraint, or at least one direction of it for ordered, that there's only one person who ordered Capellini. And in this case, if you know, okay, there's only one person who ordered Capellini and either Damon or Claudia ordered it, yeah, then Angie cannot have ordered it. So and this is something that constantly occurs. And of course, this in natural language, this is kind of implicit in the person. The person who ordered capellini, and here it's saying there is some person who ordered capellini, but this translation is fine for logic grid puzzles, because another translation that would have been fine would have been this: for all persons who ordered capellini are either Damon or Claudia, would have been equally good. But this is the one the system, the NLP tools produce. So this is the one we work with, and we noticed this really doesn't propagate very well. So you almost always need to use implicit constraints as well. I already mentioned this. We use the IDP system under the hood, and that's roughly the summary of the Ekai paper.
So I don't know if jumping ahead, but would you be able to figure out that Angie didn't order this, or would you not?
Well, so the tool would figure it out, but would say it follows from this clue together with the fact that for all P1, P2, and then pasta, let's call it something to eat in E, ordered P1, E, and ordered. So this is one of the transitivity constraints that he has. Implies, the bijectivity constraints, P1 equals P2. So he has these bijectivity constraints as well. And then he would say, okay, from this clue together with actually one bijectivity constraint, I can figure it out.
Okay, thanks.
So, either we can take a short break now, or I can just continue. I see it's, well, been 45 minutes something. So we could take a 5-minute break or 10-minute break, and then I could continue. This would be an okay moment to split the talk in two. It's like you wish, basically.
Then I say, since we're usually taking our breaks a bit late, why don't we take a 10-minute break now? So we'll reconvene like 27 minutes past the hour. But of course, before, questions. There hasn't been much by way of questions in the chat, but this is a good moment to speak up. Any questions, comments on what Bart have said so far? Please don't hesitate. So we don't see anything in the chat right now. I guess we'll just see if anything accumulates during the break. Otherwise, 27 minutes past the hour, we'll reconvene and continue the seminar. Thank you so much. So we should get started again in like a couple of minutes. Yes, it's an interesting question what the psychologically correct cost function should be.
Yeah, it's probably a very hard to answer question and very personal, but yeah.
You have to show your puzzles to small kids and then measure how many seconds they look at the clues and filled in grid point, and then depending on that you decide how deep the truth was.
Yeah, and then, well, of course, for adults it's maybe something else that's easier.
Another question is, yeah, sorry, Kieran.
There's someone at St Andrews who's doing a PhD on how humans solve Sudoku puzzles, and she's recording people solving specially crafted puzzles and looking at the logical steps they make and doing things like eye tracking to see which constraints they're looking at. That possibly provides an answer to this.
I mean, I use a lot of binary. I'm not a Sudoku master. I do use a fair number of binary clauses. Like, for this square, by the time I've nailed it down to, okay, it's either a 2 or a 5 here. And the 2 or the 5 will be in either one of these two guys.
Yeah, so I think what the first thing she established was that anyone who knew about constraint programming or SAT solving would immediately have to be an invalid experimental participant. But it looks like humans do very high levels of consistency, but only locally. So they don't write anything down, but they can look at several constraints simultaneously and reason against those constraints, as long as it doesn't involve really remembering anything except deletions.
I mean, another question is also if you want to measure somehow the depth of facts. Like you could say, because somehow the more clues I have used in order to reach a point where this Sudoku cell is filled with a 7, if this comes at the very end, then maybe somehow I'm less confident because the first conclusions are so obvious, but then when I'm starting building on my own previous conclusions, then what if I screwed up somewhere?
Yeah. And what also plays a role, I think, is if you really want to use this for explaining, is that in the beginning of your explanations, certain things will be quite hard to understand, while by the time you're at the end, people will have seen these patterns and will see, okay, they will start to see it differently. They will start to understand more. So you might get away with taking bigger steps more towards the end of the sequence.
Yeah, and can you capture symmetry? I guess you can, but using the encoding, you can capture stuff like symmetry. Like, okay, by the same reasoning we just used, I can apply it over here, and the same thing follows.
Yeah, possibly. Or but there are also sometimes, I think I have an example here somewhere. Yeah, this here is an example of some kind of a pattern that the first time I had to look at a bit from why is he concluding this? But once you see it, the next time will be quite easy. So what you see here is in this step is that, so Damon cannot have taken Farfalle and Rotini, and 16 cannot have been Capellini or Tagliolini. So basically, if Damon would be paired to 16, then there would be no options left for type of pasta. And visually, this is basically, you have the entire row filled with negations somewhere, but part of them with Damon, part of them with 16, so Damon cannot go together with 16. And that actually uses several bijectivity and one transitivity constraint. But yeah, once you've had this kind of an explanation once, and you see, okay, these rows, basically it's a complete row of minuses if we merge them. The next time it's obvious that this is correct, but the first time it at least took me a while to see what's going on here.
Yeah, so Paul Beam is suggesting in the chat that we should crowdsource. You should put out, I don't know, tons of explanations on what mechanical Turk and have them scored.
Yeah. Of of course, the question is how deep we want to go on these puzzles. But we've been thinking about it, about how to easily figure out what's the right or what are easy explanations. I think our magic numbers came up with something quite okayish, but far from, well, the actual, if it even exists, the actual cost of such things.
So we should get started, but let's just give the chat still seems to be silent, but anyone else who wants to grab the moment to ask a question before we ask Bart to get started again, please write something in the chat or just speak up. Otherwise, I guess we'll just ask Bart to continue. So yeah, I think let's just continue then.
All right, just interrupt me if something shows up, some question. So the next section, so we took a step back. We said, okay, these are the kind of explanations we want. We have some mechanism to compute them, but it's actually not really computing optimal ones with respect to our made up cost function. So let's take a step back. What do we really want? We actually, let me just put this full screen. We actually want to go beyond these minimal unsatisfiable subsets to compute something better. And when we looked into the literature, what existed, there was already some work on optimizing such minimal unsatisfiable subsets, on finding a smallest mus. That's what the S stands for, which searches for cardinality minimal mus, minimal unsatisfiable subsets. There was nothing yet on optimizing them, but optimizing them seemed quite close to the existing work. So our first step was, well, let's look at a new problem, an optimal unsatisfiable subset. So we have some arbitrary, well, we have some function, some cost function given, for instance, some linear cost function, and we want to optimize, we want to find an optimal unsatisfiable subset, meaning we have some formula, and on this slide, yes, so the T and I, the I is already considered to be part of the T here. We just have some formula. We want to find an unsatisfiable subset of it. So S is a subset of T. It must be unsatisfiable, and all other unsatisfiable subsets should have at least as high cost. That's our goal. Once we have that, so we still have to solve how can we compute these optimal unsatisfiable subsets, but it turned out to be quite a minimal modification of existing algorithms. But once we have them, we can modify our algorithm for one step and say, well, let's go over all the literals that we want to derive. For each of them, find an optimal explanation, basically, an optimal unsatisfiable subset of this here. And pick the best one. And then we suddenly have the guarantee of optimality. We can wonder how big a difference does it make in practice to go to optimal unsatisfiable subsets versus minimal ones. But actually, if we look at this algorithm, we're actually probably doing a lot of work way too often. Because all of these calls to this new thing that searches for an optimal unsatisfiable subset have a very similar theory. So they get as input something almost the same, except for one literal of a difference. And we're doing this over and over again in this loop. So probably we thought at that point there has to be some way to exploit this even more. The fact that we're doing so many calls on very similar stuff. What can we do with it? Was the question. And so essentially, if we look at it, what we want to do is, instead of for each possible literal that we could still derive, searching an explanation, and this explanation corresponds to some unsatisfiable subset. So what we're actually interested in is, well, given some formula, this formula here, this now says, so my clues hold, whatever I've derived so far holds, and why is there a disjunction here? This should be a conjunction, sorry. This should have been a big end. So conjunction over all the possible literals that we can still derive of the negation of that literal. We want to find an unsatisfiable subset of this with the special property that it contains exactly one of those literals, not L. That's what we want. So what we're actually describing here is a problem where we want to find an unsatisfiable subset of some formula that satisfies certain meta-level constraints, certain structural constraints about which formulas can be included together and which cannot be included together. And that's optimal with respect to a certain function. And we call this problem OCUS, and stands for optimal constraint unsatisfiable subset. So constraint as in we're now imposing meta constraints about which subsets are acceptable and which are not. And the O, yeah, of course, stands for optimal. So optimality now means among those subsets satisfying the P, it's optimal. And once we have, suppose that we now can somehow find some magic black box that solves the OCUS problem, computing an explanation, a single step becomes very easy because it's actually the entire algorithm is just one, well, the entire computation of a single step is just a single call to OCUS and we're done. So our life is, from the explanation point of view, we're happy now, except that now we have a new problem to solve, which is this OCUS problem. So how can we efficiently generate OCUSes of a given formula or theory? And there we took inspiration from existing hitting set-based algorithms. So hitting set-based algorithms, they're quite popular in max set solving and also for finding unsatisfiable subsets, for smallest unsatisfiable subsets. And they're all based on the following duality, saying that, well, so this theorem talks about minimal correction sets, and a correction set is something that you have to remove from a theory to make it satisfiable. So T is unsatisfiable, and it's basically a correction set is the complement of a satisfiable subset. And what is, and this also talks about the MUSes, the minimal unsatisfiable subsets. So a set is a minimal correction set, even only if it's a minimal hitting set of the unsatisfiable subsets or of the minimal unsatisfiable subsets. And it's a MUS, it's a minimal unsatisfiable subset, even only if it's a minimal hitting set of the correction sets. And this duality is often used in algorithms that basically alternate some call to some hitting set solver, that if you're trying to find, for instance, the smallest MUS, you're building up a set of correction sets. You do a lot of set calls and you're building up a set of correction sets, and then you use a hitting set solver to find the minimal hitting set of that. And then you see, look, oh, is this now unsatisfiable? If yes, I'm happy. Then I found the smallest MUS. If not, I keep on going. So yeah, this is the duality that lies at the basis of many maxset and SMUS algorithms. So we started from that duality and tried to solve the OCUS problem with it. And this is basically the extension of what I just described in words to this is our hitting set algorithm to compute OCUSes. And so what we're doing is this H here is a set of correction subsets of T. So it's initialized to be empty. And so and we will just keep track of a set of correction subsets of T. And what we constantly do is we assume that we can compute some hitting set of H that is optimal with respect to F, and that satisfies a certain integrity constraint P. And this P is just exactly the kind of meta constraint that we wanted. So H, so in practice we will use an an ILP solver here, a linear programming, but you could use a set solver here as well, depending on how you go and encode this function f and this predicate p. So we compute some hitting set of h satisfying certain constraints, and then we check, is this hitting set satisfiable, yes or no? If it's unsatisfiable, then we have the guarantee that we found an OCUS, that we found an unsatisfiable subset that's optimal with respect to f and that satisfies this p. If not, ignore line 7 for a moment. If not, we just say, okay, well, then it is satisfiable. So its complement is actually a correction subset. Not necessarily minimal, but that doesn't matter. Its complement is a correction subset. So we add it to H. And we continue. Yeah, by adding the complement, we get the guarantee that the next time to have a hitting set of H, we will not get the same anymore. And this keeps on going until we find an OCUS, if one exists at least. This here, this grow method is something that's often, well, it's something optional. So there's the opportunity here to not just use this specific S that we found, but to extend it into something larger that's still satisfiable. I will come back to this when I discuss different possibilities for this grow. But so there's this option to still extend S. And well, with respect to correctness, so the property that we're using to show correctness is, well, if you find some hitting set, so if you have any set of correction subsets of T, so you have a set of, I didn't want to erase this, a set of correction subsets of T, H, and you have some hitting set of H, so some set that contains at least one element of each of the correction subsets. And if that hitting set is optimal among the hitting sets satisfying P, whatever P is, then S, and furthermore, S is unsatisfiable, then this is indeed an OCUS, then no better one can exist. And slightly to our surprise, we're actually not using any kind of monotonicity properties. When we first wanted to prove this, we had in mind that we had to use certain monotonicity properties of P and F. And actually in the reviews also, we noticed a couple of reviewers being surprised, hey, you don't have this, but I checked it and it indeed seems to work without monotonicity properties. So there is something, this theorem might be slightly stronger than it seems at first. And yeah, this case it doesn't really happen in our explanation situation, but in case H happens to have no hitting sets because you just have a very bad P or something, then of course T has no OCUSes. So, and these together guarantee that the algorithm indeed works. So this is actually not a major modification of the existing algorithms. What we do basically is we push the cost function and we push this predicate, we just push it all down to the solver taking care of finding hitting sets, and that's it. So if we just remove this cost optimal and this FMP, you get some generic hitting set based algorithm for doing something with unsatisfiable subsets. And so we can just push them down. This function, this predicate, we just push it down to the solver responsible for the hitting sets. And then there were some further IDs, and these further IDs that we had were, well, first of all, we're not just doing one call to OCUS, and we're doing one call for a single step, but in the next step, we're going to do another call to this OCUS, and then again and again and again. We're going to keep on doing this until we have this complete solution. And actually, this second call will probably be very similar to the first call. How can we reuse information from the first call? That's what we wanted to solve. And then there's this grow. This grow, I said, okay, I just left it open for now. I said we can have some methods, we can have some max out call, or we can have something that extends this satisfiable subsets to a larger one. And there's a trade-off between how much time do I want to spend in it, because the larger we can make this as, the better it is, the more it constrains our hitting sets. but we don't want to spend too much time in it. So there's a bit of a trade-off there. As for incrementality, well, the obvious way to do it is, well, let's just keep our age. But keeping our age, so the age consists of correction sets of t. So we can, if the next time we would be calling this ocus with exactly the same t, then we could just keep the age. But what's actually going to happen is that we're constantly changing the t a bit, in the sense that in the first time we say, well, we start with t, and then and the negation of everything in I-end, the negation of everything in I-end, and the next time we might have derived one literal already, and we do it with t and L, and the negation of everything in I-end except for L. And the next time, every time one or more literals move, basically switch polarity in our call. But so we're doing it with very similar theories. And actually, what we can, in order to reuse as much information as possible, we can just view this as if we're always using the same theory. And namely this one, everything in T, everything in I-end, and everything in the negation of I-end, but we play with our P. Say, well, in the first call, you're simply not allowed to select any of these in your ocus. And in the second call, you're not allowed to select the negation of this L anymore, but you're allowed to select the L. But in that case, we can just reuse whatever's in H, so in the next calls. So since we know in advance what our complete theory might be, we can use this. If you want to do this in slightly more generality, the trick is not to keep track of your correction sets, but to keep track of your satisfiable subsets, because they will always remain valid. Even if you change your theory, you can just take the intersection of a satisfiable subset with your new theory, and that will still be satisfiable because you're only making it smaller. So if you want to use this incrementality in a different setting, you have to focus on the satisfiable subsets and not their complement. And then I already mentioned there's the Grail that we didn't really talk about yet, and so this I wrote on my previous slide already. We have this theory, we have this I-end, and we have this complement of I-end, and now we have some subset of this. How will we grow it? How will we take all three of them into account or not? And what about the cost function? Will we take that into account somehow for growing? And are we then interested in growing it to something with a small cost or with a large cost? Actually, these were all questions that we didn't really know. There were arguments to make for lots of it, for several of them, options of them. So we just tried lots of options out. And the option that worked best, we will come to the experiment soon, is when growing, we basically aim for something that's close to the actual solution of the puzzle. Meaning, so we do a call to, we want an unsatisfiable subset. We find some S subset of this that turns out to be satisfiable, but that contains at least one of these I and bar literals, so at least one wrong literal. What we then did is, well, let's try a maxset call that extends this subset as much as possible, but focuses on maximizing what's correct, making these true and making these true. That's the option that worked best. And the reason it worked best, I think, is because we were using, because basically it was very easy to always find the same solution for the set solver, something that's very close to it. Yeah, making this grow call not too expensive, but still getting quite large subsets anyway. And I think that was somewhat balancing the trade-off. The cost function, we didn't really see any. I don't really have any interesting remarks about that. We tried different versions, as you will see on the experiments, but there's not a lot to be learned there that we saw at least. So we implemented this, building on PySat and something that's now known as CP-MPy, and that used to be known as CP-Py, but for some reason that had to do with pip packages got a new name. Yes, what CP-Py does is it allows an integration of writing your CP constraints with Python data structures. And then it automatically reduces the problem to set. So it does the grounding. Okay, so but we implemented this, and then we wanted to test a certain. We had certain questions we wanted to see answers to. So first of all, we wondered this step from minimal unsatisfiable subsets to optimal ones. How does this influence the quality of the explanations? I mean, in practice, then, of course, in theory, we know we will only get better, but how much better do we get? Does it really make that big a difference or not? So that's the first thing we tested. Then we compared these different grow methods that I talked about. We also tested the difference between having this constraint version that has a single call in each step versus the non-constraint version. And we wondered, does reusing these satisfiable subsets, does it significantly influence our efficiency or not? I mean, is it important to reuse them or not for these explanations in particular? As for the solution quality, it's plotted here. So what this should have been used here is probably a cost of 50 or something for, or 50 or 60 for using a single clue, I guess, that was used here. And probably for a single implicit constraint, and probably 100, I guess, for using a clue. I don't remember the exact numbers, but what we see is that we find quite some instances that are where explanations are produced that are very much more, so where the good explanations are simply not found by this mus-based explanations generation. So it really pays off to do optimal unsatisfiable subsets. As for the grow, what we basically have here is 3 groups of algorithms. These are the ones that use a maxset call in the way I explained it before. So what they try is to maximize what's called actual stands here for finding a satisfiable subset that's as close to the actual solution as possible. And this here tries to maximize the full, takes the entire theory, everything, and just tries to find as large as possible unsatisfiable subsets of the entire theory. So notice, to make the distinction between these two, we're really using domain-specific knowledge. We're really using the fact that we're working with these puzzles, that we know that certain constraints together are easy to satisfy many of them. It's easy to satisfy many of them, while these other constraints, which are then the negations of the final literals, they basically mess up our solutions of the first constraint. So this distinction is nothing generic, it's specific for the explanations. And then there's some greedy method that just tries to grow the satisfiable subset by adding constraints. Yeah, so it's set based, lots of set calls in there. And what we noticed is, like I mentioned, that these ones perform better. And there's this last thing, the distinction between these 3 is which kind of cost function. I think the one that performed best was just giving a uniform cost and ignoring the cost function that was given altogether. But I don't really have a solid explanation for why that would be better. So just showing it here. And then if we compare the different setups, so using either Ocus, so the constraint version, or the non-constraint version that just has this loop and computes lots of OSs, and either incremental or non-incremental. And this is the mus-based solving. So first of all, notice this is not a fair comparison. These four here are computing the same thing. They're computing a sequence that's in which every step is optimal, and this last one is not. So this has an easier job, at least. And what we're basically seeing is that we even outperform with this constraintness. These are these two lines. We outperform the mus-based optimization, which is somewhere in between the constraint and the non-constraint version. What we also noticed is that this incrementality, it has some effect, not so much for this OCUS-based solving. But if we do the same trick with the incrementality with the non-constraint version, we didn't notice any difference. Basically, it doesn't make a difference there whether you do this incremental solving or not. This is also something we still have to look further into. I mean, intuitively, it would make sense that we would see this kind of benefits from this incrementality, because we're really doing lots of the same computations over and over again. So it's a bit strange to not see this show up in OS, and we're still looking for an explanation for that. Or, well, but maybe it's just a bad benchmark set that we need to expand it. That's also possible. But that's roughly the summary of the experiments in this section. Yes. So any questions about this OCUS-based explanations or about the experiments? Okay, then I'll go to the next part.
One question actually. So I was getting I guess, yeah. So I'll need another review of this to fully grok everything. But it seems to me that when you're computing, are you computing the explanations like one fact at a time?
I know that's
and
actually
then somehow
a very good
greedily
question.
choosing which one is the cheapest one to get next. Or because it's somehow, I mean, maybe I misunderstood it, but it seems to me like there might be, like, locally, some explanations seem cheap to get, but if I took another route, then I would, the overall cost of getting all the explanations might have been less expensive, or I don't know if the question makes sense.
So there's two things. So or maybe more than two things I want to say about this. But so we're computing the explanations, say one fact at a time in between quotes. But when we're explaining a fact, we explain everything. We immediately explain. Actually, in our explanation we will derive more than one fact. We will derive all facts that follow from the same clue. For instance, if you say, I can derive fact 1 using only clue 1 and bijectivity constraint 1, but from these two, actually a lot more follows, then we immediately derive everything else that follows from them as well, because it has the same cost anyway, and it's using the same information. So why not just do it all at once? For instance, a very silly example, if there's a clue saying Jacob has paid €5, that we then immediately also derive that he didn't, or maybe Jacob didn't pay more than €5, that we will not go give one explanation that says he didn't pay 1, and then in the next step, oh, he didn't pay 2 for exactly the same reason. Because, so that we do in one step. So you derive multiple literals at once. And what we do every time is really, we compute the cheapest step, at least in the OUS and OCUS-based implementations. We really compute the cheapest next step that's possible, or a cheapest next step that's possible, because there can be multiple among all the possible literals to explain. So that's really the goal. This gives us the guarantee that our final sequence will be optimal with respect to the worst cost that's occurring in the sequence. But of course, there might be, I mean, it might be possible that if you at a certain moment that you have the option between basically a sequence that has cost 4 all the time and a 5 in the end, versus a sequence that starts with 1 cost 5 and then gets super cheap afterwards. Because once you have done this hard step, everything is easy. and we're not making this distinction yet. So our algorithm will find this sequence. It will start greedily from the start and see what's the cheapest thing I can derive now, and in that case this will be a 4, and it will keep on finding all these cost 4 steps, and then say in the end, okay, yeah, but now I'm forced to do this very expensive step of cost 5 that I could already do in the beginning. So we're not optimizing this yet.
Yes, I see. Okay, makes sense. But you're right that, okay, so one thing is that I guess monotonicity with like learning new facts cannot make anything else more expensive. I guess that's, but it could also, I mean, it also goes to the, I guess, the question we had during the break about psychology, because one, you could also optimize for somehow shallowness of explanations, maybe, like, you know, how many, like, how many derivation steps do I need to reach the deepest fact? And maybe then like a shallow explanation is easier to follow for a human than one that just gets one fact at a time in a very, very long chain or something. But I guess that's like a slight detour into the main topic of what you've been talking about.
Yeah, but actually it might be related to what I will come to next, to these, what we call nested explanations. So maybe I'll just start talking about that, and then we will see that shallowness or something similar show up there. Because I think in the break, when you were talking about this shallowness, I don't think you really meant, it was in the context of Sudoku, and I don't think you really meant like how deep it is to solve the entire Sudoku puzzle. But often when people solve Sudoku puzzles, they have their grid and they start making certain assumptions. What if this were a 1? Or maybe mentally, what if this were a 1? Yeah, then this has to be a 2, and then this has to be a 3, and then a 4. But this is not possible. So my original assumption that this is a 1 was wrong, so this cannot be a 1. And in this case, if you have to do this mental process of remembering lots of stuff, and then to conclude, but it cannot be a 1, the longer the sequence is, the more, well, the harder it becomes to really be sure that this couldn't have been a 1 in the first place. And let's just get to the nested explanations, because this kind of reasoning is actually what we're doing there.
There was a question in the chat also. I don't know if Saham wants to ask it. I tried to give permission to speak, otherwise I'll read it from the chat.
I don't see it. I see a Q&A, but is there maybe a chat and a difference?
Yeah, so the question in the chat reads as follows. So would the algorithm only find the lowest point in respect to the current state? Also, is there another method of visualization for this problem? That's the question.
So would the algorithm only find the lowest point? So indeed, so what we search for, or what we did this far, is given a certain state, a partially filled in grid, find the cheapest next step. And of course you can chain them, or find a cheapest next step. And of course you can chain them to get a complete sequence of explanations, but it's quite greedy, and each step is just locally, there's no coordination over the entire sequence yet. And are there other methods of visualization? Well, probably there are, but this is actually, these grids that we have are actually quite common in these books that have logic grid puzzles. The grid is often just drawn next to it already, so that you don't have to do it yourself. So it's there, and it's the common way of visualizing these kind of puzzles. Which is why we chose this as an explanation mechanism and not natural language, because in natural language this kind of explanations, because of this clue, blah, 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 and the fact that there's only one, this tends to get quite long and unreadable. So,
okay, thanks.
Yeah. So for the nested explanations, what we noticed is that even with our cost function, some steps were still quite difficult. And of course, you might say, yeah, but that's maybe because you have a bad cost function. But the puzzle I showed you, so this pasta puzzle, it's an interesting one because it was actually sent to us by someone who knew that this master student of mine had been working on automatically translating them into logic and solving them automatically. And he had been trying to solve this puzzle from a newspaper or something, and he couldn't find a solution, and he wondered, is it even a correct puzzle? So that was his question. Is this puzzle even correct, and can you explain it to me? So if you try to solve it yourself at some point, take the time for it, you'll see that there are a couple of steps that are quite hard, and I'll show you some of them. And our idea was now, okay, these couple of quite hard steps, can we go explain them in more detail? And here's an example. So this is not one of the very hard ones, but this is one of the steps that's produced that could also be explained in more detail. Because if I were to explain to you what's going on now, so we have derived, and what's marked here in the box is a combination of implicit constraints. That's the reason why this follows. So what this says here is, well, Damon doesn't eat farfalle or rotini, and 16 was not the price of capellini or tagliolini. So we can derive that Damon didn't pay 16. Now, the easiest way for me to explain it would be, well, yeah, if Damon would have paid 16, if this would have been a yes, well, in that case, because Damon didn't take rotini, but Damon paid 16, then rotini cannot have cost 16. And because Damon didn't take farfalle, and Damon paid 16, farfalle cannot have paid 16, cost 16. Yeah, and so that means we have a line of all minuses, all impossibles, meaning that this is simply not going to work because 16, there was no pasta that cost 16 anymore. Yeah, so there's some bijectivity constraint violated here. This is how I would explain this. So we make the assumption that we make a certain assumption, and now suddenly I can split this up into single applications of transitivity and bijectivity by making this assumption. It's making my life a lot easier to explain it. And this explanation makes a lot more sense than just saying by these 4 squares and a combination of these and these transitivity and bijectivity constraints, this follows. That's quite difficult, but if I then go explain it into more detail, yeah, but what if, counterfactually, what if this were different? Then I can split it up into even smaller steps to get to a contradiction. So that's what we added then on top of the explanations to do this. And here for this example here, this is, yeah, in this visual interface, if you don't understand the step, you can say help. And say this one, I don't understand this derivation. There was only one. And then it indeed splits it up. It says, well, yeah, but from if, and this black square means this is this counterfactual assumption. If this were the case, then the 16 would not have been there. Then rotini could not have cost 16, just exactly what I've been explaining. And this gives us a contradiction with bijectivity. Maybe one of the more difficult examples. At a certain moment, this is found to be the correct or the next explanation step. Oh, by the way, everything on the website is not necessarily optimal because this is still with our mus-based explanation, but with some heuristics to guide it towards cheap explanations. So here there's no optimality guarantee yet. That's work in progress. But so what it's saying here is, the next simple thing to do is use the fact that the person who ordered tagliolini paid more than Angie. And this is always possibly in combination with some implicit constraints. And the fact that Angie didn't order capellini, farfalle didn't cost 4, and tagliolini didn't cost 16, to derive that rotini didn't cost 12. Now, honestly, if I see this, I have no clue why that's true. I mean, I believe the system because I know how it works, but this is not helpful for me as a human. So it would take me a lot of time to understand why this is indeed a good explanation step. Luckily, what the help button says is, well, suppose hypothetically that Rotini would have cost 12. Then we can just start using bijectivity constraints and see what we derive. And actually, we can use this clue. The person who ordered Tagliolini paid more than Angie, together with the fact that Tagliolini didn't cost 12 or 16, to derive that, well, Tagliolini must have cost 8, because Tagliolini cost more than whatever Angie paid, so there must be some cheaper value there. And Angie paid 4, actually, because she paid less than Tagliolini. And then we can keep on going with here the transitivity, this typical triangular pattern. Angie paid 4. 4 was not linked to farfalle, was not the price of farfalle, so Angie didn't have farfalle. Angie didn't have Rotini. And here it's a bijectivity constraint that derives Tagliolini cost 8. No, sorry, we already had this check mark. It cost 8, so it doesn't cost, so nothing else costs 8. The orange ones are the ones that are derived. And we can keep on going with basically these simple steps, completing this, and at a certain moment we find a contradiction with a transitivity constraint, because Angie paid 4. 4 was the cost of Capellini, but Angie didn't take Capellini. So we get a contradiction. So our original assumption was wrong. And this is here, what Jacob, you were referring to this shallowness. So this is not shallow at all anymore. But of course, the good thing is that we solved the memory problem, in the sense that a human reasoner, to do this kind of reasoning, this shallowness is maybe important because of remembering everything correctly if you're not writing everything down. And yeah, the steps are a bit more trustworthy now, but still this is quite a difficult thing to derive next. And that's basically what we do with the nested explanations. So for certain steps, we will produce a nested explanation. And what we do basically to decide for which steps we do it, well, we try to produce a nested explanation for all steps, but the tool will only visualize it in case the hardest step in the nested explanation is not as hard as the original step that it's trying to explain. Yeah, because that can sometimes happen. If your step is just too simple, saying I use a simple bijectivity constraint to derive that if, well, let's just take an example. I use, where do we use a bijectivity constraint? Here I use a single bijectivity constraint to derive that if 16 was the price of farfalle, then nothing else was the price of farfalle. If I go try to explain this in a nested fashion, well, what if 4 was the price of farfalle? Then I'm just going to get, well, contradiction with this bijectivity constraint, and it's going to be as hard as my original step. So in that case, you will see that the help button doesn't work because we tried to produce a nested explanation, but we judged the hardest step in there is as difficult as what you're trying to explain, so we're just not going to give it to you. And so to conclude, so what I showed you today is, well, quite a young research project. There's still lots of angles to be tackled here, but the overall goal is to provide explanations that are somewhat human understandable, or not yet, at least going all the way to so we didn't do any experiments with humans yet. Well, we're not going there yet, but it's an option to consider this as well. And for now, we've been focusing on splitting certain derivations up in small comprehensible steps, and yeah, a bit at explaining them at different levels of detail. In the context of these nested explanations, you could also go further still and say, well, within a nested explanation, introduce another level of nesting. But what you're then basically doing is, yeah, having some search, developing a complete search tree in the end. And of course, then the question is, how long can a user really follow this? What we also saw is that there were some new algorithmic needs showing up at these computing these ocuses, these optimal constraint at this set unsatisfiable subsets, and we demonstrated on logic grid puzzles. As for potential use cases of this kind of tool, we envision that it could be used to teach humans how to solve certain problems, like here this zebra puzzle. Someone who's never seen them can look at this kind of produced solutions to learn new problem solving strategies. Also probably to quantify difficulties of a problem, because if we can somehow measure correctly how difficult certain steps are, then we could quantify problem difficulty. Or in an interactive fashion with a help button that while a user is solving it gives you a hint about, well, look at this clue, because this is a clue that's going to give you a next simple step. In more, let's say, interesting scenarios, we believe this could also be used in interactive configuration or planning or scheduling tools, where there's some expert scheduler doing the scheduling, but assisted by a computer who basically is doing lots of smart propagation for him and showing him the consequences of their choices. So in this setting, it might sometimes happen that this expert scheduler thinks, hey, so I selected certain things and now suddenly I can no longer schedule this course in that lecture hall. Why is that? Explain it to me. Explain to me why you derived this. And then this kind of explanations might come in handy. Also at the time of the development of the actual knowledge base underlying such a system, it might be useful to see, this constraint that I entered is actually that we're using now to explain something is actually one that doesn't have to be enforced. So we're gonna disable this one. So this kind of interactivity, these explanations could also show up. Some avenues for future work would be, well, this has been mentioned a couple of times already. How can we learn this optimization function? And so this, how to quantify difficulty of a step, basically. Or could we also somehow know at which level of abstraction to explain things? And level of abstraction can mean two things here. Can refer to these nested explanations, but can also mean to which vocabulary do we give the user? Do we use to explain things? So which literals can be used in the explanation and which cannot? We touched upon this already. We also plan to look into explaining optimization. So explaining, if we're really tackling optimization problems, there's lots of different types of why questions that show up. And this will, for instance, and this has been studied quite a bit in the context of explainable planning already, explainable AI planning. But you have these contrastive questions like, why not this? So you're giving me some optimal solution, but why is this not in there? And then we can explain, maybe you can explain why it's not in there. Maybe there's an alternative solution where it is. Or what if I change that? How much worse does my solution get? Actually, there's a whole range of questions that you can ask. And on the one hand, we want to look into what is this range of questions? Can we come up with interesting solutions there? And on the other hand, can we make this efficient? Can we make this scale to an extent that it's really usable in the kind of interactive problems that we were talking about? And can we make all these algorithms possibly incremental to make it even faster? These are some avenues for future work, but there are plenty more showing up often. So that concludes my talk. If there are any more questions, I would be very happy to answer them.
So let me first, on behalf of everybody, thank you for a lovely presentation. This is great. I certainly do have a few questions, but I should give the chance to others to chime in first, maybe, if there are any questions from the audience. Or while people in the audience are thinking. you sketch different user cases. Just out of curiosity, how far do you think this would be from a scenario where you would actually use it for, well, maybe not these kind of cute puzzles, but for some of the application areas you were thinking about?
So,
or is it more at the level of like really foundational technology development?
We are still quite far from trying it out on a real application, say, but it is our plan to do this in a year or two, say, to really go towards some interactive scheduling, for instance, and to really try it out there. So what we've been discussing today is basically only explaining the propagation such a system does, and the question will arise: well, if we throw industrial problems at it, much larger than this kind of puzzles that we're throwing at it now, how efficient will it be? But of course, the good thing is that maybe the propagation mechanisms used in these systems might be weaker than what we're doing now, basically computing the intersection of all the models. So in that sense, there is some hope that if there's not too much to explain at one in one step, that this could still be doable. But we didn't test it yet, but it's certainly on the planning to test this on more realistic scenarios, but we didn't really start yet. So
one question I was thinking about also, you mentioned, for instance, like scheduling problems, or why one could envision other constraint problems which have two steps, where the user is first helping you to model the problem, and then gets a solution back, and then maybe the original user says, no, this is not what I was looking for. I mean, I'm sorry, but this solution just doesn't make sense. Say a scheduling of crew or whatever. And like, could you potentially use this to like say, well, you know, what's wrong? I mean, maybe I set my cost functions incorrectly so that the solver was prioritizing. Like, I can realize that where on the path from modeling to solution did we go wrong, because this was not the solution intuitively I was looking for.
Yeah, so this is, I guess, related to the second point here. So that so until now we only tackled the question, why do all of these things follow from my model, basically? But we didn't look at other types of questions yet. So I think what you're saying now is more the kind of contrastive question, especially if you would give some argument as to what's wrong. Not just this is not a solution I expect, but maybe why did this not happen in my solution? Why are you suddenly switching things completely up?
I mean, I don't know. Say you're having a scheduling problem, and you know, the way the scheduling algorithm put out my summer vacation was like truly terrible. I really want to click at it and say, what on earth are the constraints that forced you to put all of my summer vacation in December? I mean, that's a terrible decision. And then
yes.
Your algorithm will say, aha, but this was because
this reason you couldn't go in January, and this reason indeed. So that kind of thing might be possible if he was really, with what we have now, if he was really forced to put everything in December. And of course, if he chose to put certain things in December, then we cannot explain it yet. So if there was a choice and it didn't really matter, and this can happen if you just have a very bad optimization function there. If you said basically, I don't care, just plan it whenever, and then you run solve, and then your scheduler says everything planned in December, and then you get angry. Then it was basically an arbitrary choice, and we're not doing anything with that yet. Yeah.
Another thing I was just thinking about, I don't know if it makes sense, but so we've had other seminars in this and other seminar series on certified algorithms and proof logging. We have, for instance, this famous Pythagorean triple problem that says that you cannot color the integers black and white to avoid monochromatic Pythagorean triples, and you just get this big proof that is really just a syntactic object. And the question is, could you use these kind of ideas to somehow, probe the proof and maybe get some sense as to, okay, like, why are we running into contradictions at this point? Why is this construction not possible? Please explain to me which constraints come into play.
So my feeling is that there might be some nice relation between the two, but I cannot really pinpoint exactly where. But I somehow have the feeling that there are things to be learned in both directions. For instance, if we could construct some, I'll say, computer readable proof, and maybe we can abstract it. If we have some user vocabulary, symbols he knows, and then we have a computer readable proof that uses all the auxiliary variables as well, maybe we can abstract a human understandable proof from it, and that's then certified. Or something else that might be useful is that we go certify all of our steps. So we're now saying, well, here's a sequence of explanations, and the sequence at a high level can be followed by a human, but maybe it's also useful for him to have the guarantee and that each step is certified. So there's another possible interaction between the two. But I have thought a little bit about this, but not so long yet. But my feeling is that there might be some nice correspondences. We're just catering to a different audience, basically.
Mm-hmm. How much did you think about, like, what methods of reasoning does one want in the propagator? Like, what do we want the propagator to understand? I mean, we talked a little bit about symmetries. Should counting arguments like come into play, or what are your thoughts on how much did you think about like the underlying reasoning engine in some sense?
Mm-hmm. So the engine that derives that certain things follow. Actually, what we did now is completely agnostic of what this propagator can do. If you have a very strong propagation mechanism and you so basically I always used entailment, this entailment, but you can just replace it everywhere by propagation can derive that with any propagation mechanism you want, and the steps then work, of course. And that might also be interesting from a perspective of a human. I mean, if you make your propagation mechanisms weaker, you might get closer to or if you get them at the right level for the human, basically, the kind of, if you can match your propagation mechanisms to what a human can do, and then you say, well, from this constraint, this fact follows, then the human will say, yeah, okay, because I can do the same type of reasoning as this propagator, and indeed it follows. While if you have a super strong propagator that combines a couple of clues together and says from these clues together this follows, the human might be perplexed and might need this form of nesting. But so this has not yet been one of our concerns, the actual propagation mechanism.
I see. So I don't see, I guess finally the final call for questions from other parts of the audience, while I ask what I believe is my final question, maybe. So far in these experiments that you run, how much of an issue is the actual computational hardness, that the problems actually get hard to crunch, or this is like the problem so far has been elsewhere, or?
So with our original implementation, we really even on these puzzles already, we bumped onto the problem that for certain puzzles it took hours to produce this explanation, so while it wouldn't take me hours to solve this puzzle, so in that sense this was a bit yeah.
Is it clear what was there some kind of hard problem or just an unfortunate algorithmic choices or like?
Well, no, this Ocus problem is at least hard on the second level of the polynomial hierarchy. I think it will just be what is it, sigma p2 complete, I think, but it's at least hard on the second level of the polynomial hierarchy. So there is some hard problem involved there. And to generate an entire sequence, we're doing this as many times, worst case, as there are literals. So solving this type of problem. So we're yeah. If our problems scale up too much, we will get into trouble with that possibly. So, and I think to really feel this, we just need to try it. We just need to try larger instances and see whether these problems really show up. And then looking at approximate algorithms is also on our agenda to really make it scale still, to maybe sacrifice optimality again, but have some guarantee of being close to optimal. And yeah, to live with that. I guess if you do this on interactive scheduling problems and so on, you might be able to live with a good enough explanation instead of having the guarantee that it's optimal with respect to this function. I see that some hand popped up in the meanwhile.
Yes, that's interesting. So there's a hand up by Carlos. Please feel free to just unmute and ask your question, Carlos.
Okay. Yes, I have a question about your. Can you hear me? Yeah.
I can hear
you well.
You still look muted. Zoom still tells me you're muted, but I believe that you're talking. So.
Okay. Good. So I have a question about your introduction. So you were mentioning that more or less that we should work on richer or higher formalisms to don't lose the structure while we are converting. If we are converting to CNF, there is some structure that we are going to lose. Okay. That's fair enough. This is this is the case all the time that we lose that structure. But what about the structure that the user is not aware of? So what worries me is that the important structure is that the structure that the user is not able to see. So it is placing some constraints together. And then because of the conjunction of these constraints, it arises a new structure that the user is not going to see. But with sample processing techniques and detection techniques in the CNF, you can derive that structure. Also, when you take some decisions and you generate a new subproblem, you can derive that structure, but the user is not aware of that. So there is a simple example. You take the old if constraint, you take some decisions, and then you see a pigeonhole. Okay. So this is a very simple example. So I was wondering, this is like programming in a high-level language like Python and doing some optimizations at the level of assembly, you know? So maybe you want to have both things. That was my message on this.
Yeah, I think you definitely want to have both things. And what you definitely also want, I think, is detecting the structure at a high level. So the structure that the human is not aware of, that's maybe not the case when you do the choices and then end up with a pigeonhole. But if there are a couple of all different and you can combine them already at just by looking at them, you can see some structure that the user might not be aware of, but that's actually there. If you can see it at a high level, it's probably easier in the sense that you're not paying for your data complexity. You're only looking at your high-level specification, and you can ignore your problem size, and whatever you can derive from that is already nice to have. So I absolutely agree. I think we should have both, but certain things, that I've been doing, I always felt like, well, I'm really trying to detect something that was there in the first place. The kind of symmetries we've been looking at, this structure must have been there. It must have been visible in the first order representation, but it just got lost. And it feels like a shame to let this structure disappear. But of course, there are instances where you cannot just see it, and then detection mechanisms are still needed.
Okay, thanks a lot. Great question. Do we have, I guess this is the final chance, at least for today, to ask more questions to Bart before we officially declare this seminar to be over. I should mention, as the link is in the chat, that registered workshop participants are welcome to meet in Gathertown at the Simons Institute after the workshop. But I think I don't see any more questions, and we've certainly kept you working for quite a while, Bart. So thanks so much again for a wonderful seminar.
Thanks for the invitation. It was nice to be here.
Okay, thank you so much for today. Bye-bye.
Bye.